This problem is really similar to the other massive pulley problem. We have a pulley, we've got two ropes hanging from it, we've got M1 on one side, M2 on the other side, and M2 is bigger than M1, so the whole thing's going to rotate this way. So we can easily write the free body diagrams for M1 and M2 just like before. We have M1G and tension number 1, and we have tension number 2 and M2G just like the other problem, and then we can write equations. Tension number 1 minus M1G is equal to M1A. Sorry about that little dot. And tension number 2 minus M2G is equal to negative M2A, because M2 is going to go down. Then, just like we did before, we're going to draw a torque diagram. Here's a picture of the pulley, and it has forces on it just like we drew before. We have T1 pointing down, T2 pointing down on the other side. That's the two tensions here and here. We also have the weight of the pulley itself, which I'm going to call capital M times gravity, and whatever's holding the pulley up, some force upward. And just like before, we're going to do the lever arms, and the center of rotation is going to be the regular place where it would rotate on its axis. And because the force holding it up is applied right at the axis, that has no lever arm. And the weight also has no lever arm because it's applied right at the center of mass. And so that means the only two forces that have lever arms are the two tensions, and the lever arm is the radius, just like we did in that other problem. Then we put our angles in. They're both 90, and we know that the sine of 90 is 1. So when we do torque equals RF sine theta, we don't have to worry about the sine theta part, right? So we can write our equation, which is for torques, it's torque equals I alpha, right? So there are two torques. There's the T2 torque, which is going to win out over the T1 torque, right? This one's bigger and it ends up rotating clockwise, right? So I'm going to make the torques RT2 minus RT1. They're in opposite directions, and T2 wins, right? And that's going to be equal to I alpha. All right, this problem asks you to calculate I. And you might have thought earlier that, well, I just go to the list of formulas and I find out that I is equal to 1/2 mr squared. And I don't have to do all this nonsense with all the diagrams, right? I can just plug into this formula. But that's not true, and there's two reasons why. One reason is that they didn't tell you the mass. And the other reason is that they also did not tell you this was a uniform disk. They just said it was a pulley. And so you can't use the formula for a uniform disk if it's not a uniform disk. So we are going to have to plug into this formula. Now, in here, we're happy that we have I, but we don't have alpha right now. We don't have T, either one of the T's. So we need to plug in for all three of those. Well, one thing we know is that the linear acceleration is equal to the angular acceleration times the radius. That means that alpha equals A over R. And then from these two equations, we can get equations for the tensions. This equation tells us T1 is equal to M1G plus M1A. This equation tells us that T2 is equal to M2G minus M2A. So I can plug those in for those two, and I get an equation that looks like this. R times T2, which is this one, M2G minus M2A, minus R times T1, that's this one, M1G plus M1A, is equal to I A over R. See, this one went in there, this went in there, whoops, went in there, and this one went in there. Okay, and now we have one equation that we know everything in there except for I. So we can solve this for the moment of inertia.